All right, well, good afternoon, everyone. On behalf of AFAA New England, I'd like to thank you for joining us. I'd like to thank Fitzmyer and Tachi for agreeing to come on and give us a presentation about speech intelligibility. First of all, I'd like to thank our sponsors, Fire Command Systems, J&M Brown Company, Mammoth Fire Alarm, the Noel Service Company, Siemens Smart Infrastructure, Space Age Electronics, and TC Life Safety. Without our sponsors, we wouldn't be able to do a lot of the great programming that we offer. So thank you. So I'd like to thank our guests, Cameron Valeo. He's the Electrical Engineering Manager at Fitzmyer and Tachi Associates, graduate of Merrimack College with a BS in Electrical Engineering. Cam is licensed in all of the New England states, as well as New York, North Carolina, Georgia, and Texas. He has over 14 years experience in the design of electrical and fire alarm systems. In his role as Associate Principal Electrical Engineering Manager, Cameron serves as head of the electrical discipline within the technical team. With a diverse project-based background that includes lead electrical engineering and project management, he's served as a team leader and mentor for staff. Cameron has a broad spectrum of experience for new construction and existing building renovation, with a specialty in design for healthcare and critical operations facilities. Andrew Ciccarello is a fire protection engineer with F&T and has 5 years experience in the design of fire protection and fire alarm systems. He is a graduate of Wentworth Institute of Technology with a BS in mechanical engineering. In his role as fire protection project engineer, Andrew actively leads the design of fire protection and fire alarm systems for new construction and existing building renovations. And with that, I'll turn it over to Cam and Andrew.
Thank you, Jerry. For those of you that don't know us, F&T is a full-service engineering firm which provides mechanical, electrical, plumbing, fire protection, and low-voltage designs. Additionally, we can provide commissioning, co-consulting, life safety reviews. Been around for 60 years, and have provided engineering services throughout the nation for healthcare, academic, commercial, science and tech, transportation, and many other markets throughout. All that being said, we're not acoustical engineers, so the focus of this presentation will be based in code design requirements with the goal of efficiently acquiring a permit and a certificate of occupancy at the end of construction. As Jerry mentioned, we'll be discussing speech intelligibility for emergency communication systems today, although speech intelligibility has certainly been around for a while. It's not a new concept of fire alarm. Emergency communication systems are becoming more prevalent within buildings these days, and there's still confusion on the design and installation of these systems that often leads to permits not being pulled on the first try around, or adding additional devices at the end just to meet that intelligibility requirement. So the primary goal is to provide a system that is easily understood by the occupants, so there is a safe egress from the building. But we also certainly want to make sure that we are obtaining those permits and certificates at the end. In order to achieve these goals, we truly need to understand what speech intelligibility is and how to best achieve it. So today, the agenda being the basics of speech intelligibility in emergency voice and communication systems, in alarm communication systems, and the NFPA 72 requirements regarding intelligibility will be reviewed, including the acoustical distinguishable spaces, which is key to knowing where we should be putting speakers that need to be understood. And that's probably one of the biggest things that people don't accurately do. The general spacing guidelines for speakers, and then we'll kind of dive a little bit into the testing methods and requirements for that. So our discussion today will be based upon the International Building Code. We're going to be looking at the 2018 edition of that, NFPA 72, of course, and the code references you'll see within this are based off the 2016 edition. And certainly, since I'm an electrical engineer, National Electrical Code, and we're not going to dive deep into the National Electrical Code, but understanding that all of these systems the conduit, the wiring has to be installed in accordance with the National Electrical Code. So where do we start? We're looking at where is emergency voice and alarm communication systems actually required. And to get that, we review the International Building Code, and specifically in section 907 is where we get our fire alarm and communication requirements. So looking at that, the building occupancies that are required are Group A assembly occupancies, Group E for educational, your elementary schools, higher education, special amusement, looking at your bars, your clubs, those kind of setups, obviously high rises. But then we also, as a firm and as a practice, we like to recommend that within Group I and Group N occupancies that we're also providing an emergency voice and communication system, because it is critical when you think about what those environments entail. So Group I1 occupancies are rehabs, assisted living facilities, group homes, halfway houses, those sorts of things. Group I2 occupancies are detox facilities, hospitals, nursing homes, psych hospitals. These occupancies often have patients that don't support themselves and rely on the hospital staff to ensure their safety. So the hospital staff needs to be clear on the instructions, as these types of occupancies also tend to be designed in private mode, where you're not broadcasting this message across the entire building. You're understanding where the issue is, and then the facility staff is making a conscious decision of how to evacuate the patients along with a plan with the fire department. And being able to selectively do that and safely get patients and the hospital staff out of the building when they need to be. And occupants within Group M, so your mercantile occupancies, your stores, there's a tendency within these environments for people to just assume that the fire alarm is a false alarm, and they don't actually react when the fire alarm goes off. So a voice evacuation system within these types of environments is key to let people know, yes, there is an issue within your area and you need to evacuate. Otherwise, they're going to go about their business, assume that everything is fine, and then there's issues, potential issues there with the fire department coming in and helping them out, or just people getting stuck. So then, the requirement for intelligibility when it comes to is within Chapter 24. And really what this gets at here is just telling you more of what this initial portion, telling you more of what the building code is telling you, which is this needs to be your voice evacuation, your emergency communication system needs to be intelligible and it needs to be audible. So when you look at your emergency voice communication systems, it's, we've talked a lot today about the in-building fire emergency voice communications that are required, but there's some confusion that starts here about really what is intelligible, what does that truly mean, and how do we achieve that? Next slide, Andrew. So thinking about what is intelligibility, it certainly shouldn't be confused with audibility. So now that we can understand that intelligibility is required, what is it? What exactly is it? And audibility is really just, can it be heard? You don't have to understand what the message was. You don't have to understand anything about it. And the basis of fire alarm notification design was mostly that. It was based off of the audibility. Can you hear it? Make sure everyone in the building, depending on where you are, hears it. And so that's more of your horn systems, your chimes, those sorts of things. A voice system, although it applies because it needs to be loud enough for people to hear, it's not truly intelligibility. So sound level and the second question here, can intelligibility be modeled? And yes, intelligibility can be modeled. There are softwares that can model the intelligibility, and we'll get a little bit into that. However, there is no requirement in NFPA 72 or the building code that says you have to model it. It's just in certain difficult environments like gymnasiums, it makes sense that you should. I mean, it's really difficult to achieve intelligibility in large open rooms, in concrete tunnels, those sorts of things. And we're not planning to specifically talk today about the modeling software, but it's certainly a really good topic to have on its own and dive deep into, because there's so much that can be done with that. And so NFPA 72 doesn't require quantitative measurements of intelligibility, but Annex D of NFPA 72 does provide guidelines on the planning, design, installation, and testing of these systems. So kind of going back to the audibility question, it's, so, what is audibility in that sense? It's just ability to be heard. And so when we look at the requirements for intelligibility, your first point is, can it be heard? And you're just meeting those standard requirements in Chapter 18 that talk about being 15 decibels above ambient, as well as a maximum of 115 decibels for 60 seconds within those tough environments when you think of manufacturing or transportation tunnels and those sorts of things, where it really becomes difficult to not just achieve audibility, but intelligibility is almost impossible to get within those environments. So looking at how NFPA 72 defines intelligibility in Chapter 3, the first definition here, intelligibility itself, it's not very clear, but the quality or condition of being intelligible. So intelligible really is capable of being understood, comprehensible, clear. So what that really means is, to what degree do we understand spoken language? What words are we just hearing that there's words and we're getting close to it? It's truly understanding what's being said, taking those instructions and moving forward with them. So looking at what affects intelligibility, there are 5 major factors in how intelligibility is affected. Your first being your speech signal to noise ratio, which is noise causing a masking or obscuring of the voice signal. Speech intelligibility decreases rapidly when forced to tolerate large amounts of noise. So this is stuff that's generated within the system itself, either from feedback from the mic being too close to a speaker, or from some other means causing noise to build within the system and degrading that voice signal that's going across it. Reverberation and echoes are very similar in that respect. Reverberation, sound reflections that have the effect of smearing or blurring speech. Echoes is the same thing. I mean, reverberation is coming off of multiple angles. Your echo is you've given a message, it's gone into the room, the message has stopped and is bouncing kind of back at you. And certainly reverberation and echoes are greatly affected by the architecture within the building. So this is really how it gets generated. You're looking at the material of your walls, the heights of your ceilings, the material of glass. the geometric shapes within that architecture, furniture within the room, they all have effects on the echoing, the reverberation, and there's ways to help reduce that. And a lot of it comes down to coordinating stuff with the architect to understand how that might impact the overall design. Distortion is electrical or electrical acoustical components in the sound system generating noise. Again, something from within the system, usually caused by damaged equipment, your speakers being damaged, improper termination on the wiring at the speakers themselves, wire being cut or damaged somewhere else within the system, all causes for distortion within your system. And certainly, one of the biggest things is the human factor. How someone understands the message and how someone speaks into the mic. Certainly how someone speaks into the mic and how someone's delivering that live message, they can be trained on that to enhance the intelligibility of them speaking into the mic and trying to get that message across better. So this schematic is a graphical depiction of the message being delivered from the source to the building occupant, kind of going those 5 factors that we just talked about. As you can kind of see from this graphic starting on the left, we have the potential for the human factor delivering the message from the head end unit, the fire alarm control unit. Once the message kind of leaves that system and reaches the speakers, there's potential for distortion in those speakers due to faulty wiring, improperly installed appliances, poor wiring connections, damaged speakers, all of that. And then once the message is actually emitted into the room, the sound wave is potentially subject to echoes and reverberation due to the architectural materials, geometry of the space. Then once again, we have the human factor at the end, after you've had all this potential for error and mistakes kind of leading up to before someone actually hears the message. How does that distort? How does that impact what they're actually hearing at the end of it? Given all that can go wrong from start to finish, it is important that we kind of define what areas are really required to be acoustically distinguishable spaces, so that achieving speech intelligibility can be a focus of the design only where it is actually required, as well as understanding that where these locations that you can't actually achieve speech intelligibility. So Andrew will now kind of go into the acoustically distinguishable spaces.
So one of the first steps when you're designing a voice intelligible system is to start getting to acoustically distinguishable spaces. So an ADS are basically just parts of a building or an area of a room that are designated by the designer to achieve a certain notification goal in that designated space. So there are no actual requirements on what rooms require intelligible notification or not, and so that decision is up to the designer and with the approval of the AHJ. So typically, for example, for what we do, like waiting rooms, corridors, and other public spaces will typically have speech intelligibility to give direction to people who may not be familiar with the building. So an ADS can be defined by either like the walls of a room, or for larger rooms, the space can actually be subdivided to provide intelligible zones where occupants could actually move to a certain location in order to understand the message. So some considerations to take into account are the space you're designing. The geometry of the space, like how Cam was saying, the ceiling height and how large the ADS is that you're trying to provide intelligibility to. The surfaces, it's always good to ask the question and to look what the surfaces of the ADS are. So are the floors and walls bare concrete, or is it like an office area where you have carpeted floor and ACT drop ceiling, where bare walls, concrete ceilings, and concrete floors are definitely going to be harder to obtain intelligibility than say an office area with those carpeted floors and ACT drop ceilings, because there's a lot more stuff to absorb the sound waves. So another level to go into the ambient to ADSs are to look into what the ambient sound level, what the expected sound level is of the space that you're trying to provide coverage to. So that kind of speaks to the audibility part of intelligibility, where the occupant needs to hear the message in order to understand it. So in some occupancies, it's good to ask for a client's emergency response plan. These are good for where occupants that work in the area, that work in the building, or they're familiar with the building. Like an example is like a manufacturing plant. Basically, like an emergency response plan is how the client plans to train their employees in the event of emergency. If the client does not have an emergency response plan, it might be good to provide an outline for one during the design. So for example, a good spot for an emergency response plan could be in a manufacturing plant, where the manufacturing floor could have very loud ambient sound levels, and the occupants could be wearing protective ear equipment. So this provides a lot of specific challenges for the designer for voice intelligibility and audibility of the system. So you could work with the client to provide an emergency plan that would train occupants to follow a certain procedure in the event of emergency. So for example, the workers could see strobes flashing, and then once they see those strobes flashing, they're trained to move to a certain location designated as the intelligible voice ADS zone on the manufacturing floor, where they would remove their ear protection. And then at that ADS, they could get that intelligible voice message to understand the threat and then react accordingly. Acoustically distinguished spaces are a huge part of designing intelligible systems. They should be on every job, pretty much no matter how large or small. These ADS plans avoid like a lot of misunderstanding in the testing phase and the approval phase, and it clearly defines a goal to the contractor and the AHJ and the client when installing systems, so everybody knows what is supposed to happen in every space in the building. Later on, we'll touch on some possible solutions to obtain intelligibility in some unique design environments. So one of the first questions you should always ask yourself is, what is the notification goal of the room or space in the building that you are designating as an ADS? So you want to think about the type of people that are going to be typically occupying that room. Some questions to ask are the members of the public? Are the members of the room going to be the general public that are unfamiliar with the building, or are they trained employees that know how to react at the sound of a fire alarm? So here we're showing a picture of one of our plans. This is an example of what we do for an ADS plan. So we actually assign a certain lettered key note. Usually it's like A through E. And then each lettered key note relates to a certain ADS. So for example, here we have the waiting room and the bathroom off the waiting room. So typically in waiting rooms, we'll provide combination speaker strobes. So our design intent is to provide visual notification with tone alert. So say like a Tempora 3 signal, and then an intelligible voice message will be said. And in that waiting room, we're intending for the intelligible voice, for the voice message to be intelligible. And then another ADS that we specified is the waiting room, the public bathroom off the waiting room. So our intent in that area, because it's a public bathroom, it requires visual notification. Our plan there is just to provide a visual only device, and then tone alert and voice from the adjacent waiting room space will be heard through the walls. It's not our intent for the voice message to be intelligible in the bathroom. It might just happen by default, but again, that's not our intent. Our intent is for them to be alerted by that visual signal and to hear the tone and voice message, but again, it may not be actually intelligible in that room. So that's why it's good to distinguish what you plan on the occupant hearing in each ADS. In section 18.410, it gives some good examples of some rooms and buildings that may not require intelligibility. There's also a helpful decision tree in this section that kind of helps you, kind of walks you through on like how to make the decision on if the space requires intelligible voice or not. So getting into the spacing of speakers, there's really no prescriptive spacing requirements laid out by NFPA 72, like how they have for visual appliances. There is kind of a basic rule of thumb in 72. In Annex D, they have speaker spacing is directly related to the ceiling height. So it gives a recommendation of either doing a 1-to-1 or a 1-to-2 ceiling height to speaker spacing ratio. So therefore, if there was a 10-foot ceiling height, and then the speaker spacing would be 20 feet. So it's just double, the speaker spacing is double what the ceiling height is. So I wouldn't recommend using this method in difficult environments with a lot of hard surfaces where, say, reverberation and echoes would be an issue. It's definitely a good quick starting point and could definitely be used in areas where reverberation and echoes and the environment is kind of conducive to speech intelligibility, like how they would have drop ceilings, carpet floors, areas like that. So getting a little bit more in depth into speaker spacing requires a bit more thought, but the goal is the same. So the goal is basically to provide an intelligible fire alarm notification system, is to have a uniform distribution of sound to the occupants while limiting like reverberation and echoes and increasing the signal to noise ratio. So the first step is determining the critical polar angle of the speaker coverage cone. So every speaker should have these polar plots here, and these polar plots depict sound pressure losses at different angles. So in these charts, there are basically two values. There's a polar loss, which is given from the polar plot, and then the distance loss, which is calculated from the angle that's chosen. So you can see all those different angles. When you get, the further the angle is, the more loss there is, just because, you know, the further away you get from a speaker, the quieter it's going to sound. So it's actually calculated through that equation that I have there, 20 times the log of the cosine of that angle. So a rule of thumb when choosing the critical polar angle is to have a total loss not greater than 6 decibels. So that's the polar loss and the distance loss added together. Typically, for a lot of the basic speakers, the average angle that you can choose is about 60 degrees. So you can see that that total loss in that chart is actually 9 decibels, which is greater than our target of 6 decibels. But however, you have to think about that these speakers are going to be spaced next to each other. So there'll be another speaker that'll actually, its sound wave will actually add to that 9 decibel loss. So when you add the two speakers, the 2 decibels together, it becomes 6 decibels. So that loss is then within our target for what we're trying to provide. So the next step in determining the actual listening plane of the occupants. So typically the listening plane is going to be at 5 feet above the ground. This relates to section 18.431 in NFPA 72. In that section, it basically just requires sound level measurements be taken at 5 feet above the floor. It's typically at 5 feet above the floor because that's the average sound level, that's the average ear level of the occupants. So at that listening plane is actually where you want the speaker sound cones to intersect, which goes back to like the angle that you choose and everything. So this way the sound distribution is uniform throughout the space. When you have cones intersecting, you don't have basically large sound changes as you're walking throughout the space. Like for an example, if an occupant is directly under a speaker, they're going to hear a higher sound level than an occupant at the edge of the speaker, just due to the distance away from the speaker source. So if they're spaced too far apart and the cones don't intersect, then you're gonna the occupant's going to hear larger changes in sound levels due to the large changes in distance, which isn't advantageous for speech intelligibility. You really want it to be a smooth transmission throughout the space. So the last step is to determine the power rating or the TAPS rating on the speakers. So this should be related to the ambient sound level of the environment that you're providing speech intelligibility to. So in NFPA 72 and section 18431, it requires that public mode signals have the sound level of 15 decibels above the average ambient sound level of the space. So typically speaker manufacturers have sound pressure levels in a chart on their cut sheets that are measured at 10 feet away from the speaker. So it's important to realize that you lose 6 decibels per doubling the distance to the occupant. So in that picture that I have there, at 10 feet directly below the speaker, it's putting out 81 dBA. So at 20 feet, you would actually reduce that 81 dBA by 6 decibels, so you would then have 75 dBA. And then if you double the 20 feet to 40 feet, you would then lose another 6 decibels, and then you would go so on and so on. So the average sound level of a space, there's a chart in NFPA 72 that gives you some basic ones. It's I believe it's table A1843. In some unique situations, you might actually want to go in and try to measure the ambient sound level of the space, but typically with the chart, you can get away with looking at the basic versions of them. So here's an example to show you the speaker cone coverage area and where they intersect. So where you see where those triangles intersect is where that listening plane is. So there's 2 different ceiling heights here. The area on the left with the higher ceiling height actually requires less speakers than the spacing at the lower ceiling height. That kind of directly relates back to the doubling of the spacing in relation to the ceiling height. So if you get a 15-foot ceiling height, you're going to have 30-foot spacing versus a 10-foot ceiling height, you're going to have 20-foot speaker spacing. And at that intersection point, again, kind of relates back to the uniform distribution of sound. When that occupant's walking through that room there, they're going to be experiencing a smooth sound level as they evacuate the space. It is possible to have to space your speakers so the sound cones don't overlap. This isn't typically recommended unless sound modeling is done to ensure speech intelligibility is attainable, because the environment plays a big role into it. So, I mean, if you have an environment like an office area that's very conducive to speech intelligibility, then you might be able to get away with spacing them a little bit further apart where the cones don't fully intersect, because it's always a goal to provide these speech intelligibility systems to work, but to also do it in a cost-effective manner. That way, it's always a good way to get that assurance to run a sound model to kind of get an idea that you're on the right track. So typically only ceiling speakers are talked about in speech intelligibility, but wall speakers can also be used. There are a few differences to spacing wall speakers and ceiling speakers. The main difference between the two would probably be the speaker to listener distance. So instead of that 5 foot above the floor, that doesn't really make sense for a wall speaker because it's already mounted at that, I think it's 90 inches to 86 inches above the floor. So that wall speaker is already in that occupant's kind of 5 foot listening plane. So the way you think about it, instead of that 5 foot listening plane, is you have to think about it depends on the occupant's location in the room. So coverage now must be done with the occupant assumed to be at the farther distance from the speaker inside the room. So instead of the 5 foot listening plane, it's actually taken at 3 feet off the opposing wall of the room. So in a room with speakers along a single wall, the new listening plane would be 3 feet off that opposite wall. that whole coverage cone and the polar losses, that's all the same technique as done with the ceiling speakers. It's just translated to the wall, but it's overall the same technique. There are some recommendations in some application guides to where rooms are greater than 20 feet wide, they should be covered with speakers on both sides. That way it better distributes sound. There are also some advantages to using wall speakers. For example, in narrower spaces like corridors, the speakers are actually closer to the occupants and they can be set at lower tap settings or decibel settings, and could still accomplish that 15 decibels above the ambient sound level. Some disadvantages are they can be obstructed by a lot of things. That's going to be tough to kind of take into account, like if there are cabinets next to the notification appliance and so on and so forth. It can kind of mess up what your intelligibility in that room. So typically we kind of shoot to be to install with ceiling speakers, but again, it's always, you can use wall speakers as well. So getting to some unique environments here. So some environments pose very unique challenges for the designer in order to achieve speech intelligibility. So gyms is one example where they have loud ambient sound levels. There's also a ton of hard surfaces in the gyms, and these hard surfaces again create reverberation and echoes, which aren't ideal for speech intelligibility. There's also PA systems that you want to think about. Basically, you want the fire alarm system to take priority over the PA system in the event of emergency. So it's a good thought to interface the PA system with the fire alarm system in order for it to do that. And also, like, an interesting thing to take into account too with spaces like this is, typically if this was a new building, the testing would happen before the occupancy stamp is given to the building. So there's going to be a lot of empty seats, a lot of surfaces that the sound can reverberate off of, but in the actual application of it being used, the space that gym is going to be packed with people. So actually those bodies are going to act as cushions to the sound and would actually help the sound intelligibility, because the sound waves won't be reverberating off all those empty chairs and hard surfaces there. So it's just a thing to think about when testing areas like this. So in the next slides, you kind of see that reverberation is a big issue in these unique environments. Some techniques to combat reverberation could be moving speakers closer to the occupants and then reducing the taps or decibel setting on the speaker. It could also be increasing the speaker density, so making the spacing a lot smaller and then reducing the tap settings. That way you can create more coverage overlay in those speaker cones that I was talking about earlier. It's also, sometimes it's good to seek help from sound specialists and vendors that can that provide higher quality speakers than your average, say simplex or notifier wall mounted or ceiling mounted notification speaker. It's also recommended to do sound modeling when designing environments like this. It's really hard to design them with the regular speaker coverage spacing that I was talking about earlier, just because these areas are so unique. It's a really good idea to run it through a sound model and to accurately sound model it. That way you can have a good idea to distinguish, okay, are my regular notification appliances going to work, or should I consult a vendor to get a higher end speaker, basically, that is specially designed for lower reverberation and to provide that better intelligibility for the space. So another example is a subway tunnel. Kind of a lot of stuff is the same with the gym, with a a lot of the hard surfaces is going to cause reverberation, and again, it's going to be a loud ambient sound level. So some of the same solutions for the gym apply for the subway tunnel as well, where subway tunnels are probably one of the worst spaces for reverberation, just due to their typically low ceiling heights and just concrete walls, concrete ceiling, concrete wall, steel tube subway, going to create a lot of reverberation there. So it's always just keep in mind that sometimes the solution isn't always going to be with the regular speakers that you're used to using on all your jobs, that you might have to look elsewhere in order to get a special speaker to provide that audibility where the occupants are going to hear the signal and it would still be intelligible at that high level of sound level. So going back to the manufacturing plant here, again, big, large open space, a lot of hard surfaces, high ceilings. Employees could be wearing ear protection. So the kind of unique situation here is the going back to the emergency response plan. So in situations like this, if you are going to provide an intelligibility system, it's definitely worth coordinating with the client an emergency response plan to try to train the employees or see what their already previous training is. That way you can design your notification system to kind of adhere to their training, where you can specify a certain ADS zone. I mean, the ADS zone could even be around one of those pillars or columns shown in the picture there, where employees step away from their workstation when they see visual strobes going, and they walk to a designated pillar where an array of speakers could be, and they could actually understand the intelligible voice message there, so they could react to it. And also, it's also good to look at it and say, is intelligibility actually worth it? In some of these areas where it's not actually required by code, it might be worth just using a horn strobe system instead. So you don't want to push intelligibility where you don't have to in some cases, but it's just something to think about. And then moving on, Cam's going to talk about some measurement and test methods from Annex D.
Thanks, Andrew. So now that we've kind of established the design requirements, how to lay out the speakers to help us achieve speech intelligibility during the design process and the construction process, now we're kind of looking at how do we verify, how do we test and measure that speech intelligibility. And there's no specific requirements, but Annex D of NFPA 72 lays out the basics of it, how to set it up, achieve certain levels. And there's two basic categories of intelligibility testing and measurement. There's the subject-based test and the instrument-based testing. The subject-based test involves utilizing building personnel, AHJs, design engineers, to listen and interpret from the system to determine intelligibility. So a signal is going to be, words are going to be put across the system. So looking at the two methods that I have listed, there are more than the two, but these are the more common ones. The phonetically balanced word test, which is an ANSI standard test that takes 20 50-word lists that are phonetically balanced and puts that across the system. And the listener's task is to respond to what they're hearing and write those words down. And the test is based on, the results of the test is based on how many words are actually completed correctly. And then there's the modified rhyme test, also an ANSI standard test that consists of 50 rhyming non-syllable word sets like pin, sin, tin, fin, din, win, that get broadcast across the system. Same scenario as the PB test, where you're having your listeners listen and then repeat back those 6 rhyming words presented to them to see if they heard them correctly, as a measurement of the intelligibility of the system. But when you start to look more at the instrument-based tests using speech transmission index and the speech transmission index public address, are special audio signals that are played over the emergency communication system. So they're not specific words, but they're tones that help distinguish in actual intelligibility that is being received by a sound measuring device. And it gets broken down into a range for the STI, the STI-PA test, from a range of 0 to 1 across the 8-octave range of sound. Andrew, jump to the next one. So looking at the instrument test, this is a typical setup. You have your signal being generated at your fire alarm control panel, and you are taking measurement locations throughout the space. As you can see, the speakers for the fire alarm system are ceiling mounted, as we typically recommend and as usually done for voice evacuation systems. And you kind of go by more of the recommendations from the manufacturer on where these testing points are. And you have to achieve a certain level on your STI scale. So we jump to the next slide, Andrew. So these are just some of the typical meters and talk boxes used. The talk box is what's like to generate the signal for the instrument test, and no specific one I would recommend over the other. It's again not something that we as the engineer are actually performing this test right now. So these are just some generic ones that we found and have seen being used for these tests. And this goes without being said, but performing the test must be done by qualified personnel. NFPA 72 in Annex D talks about person performing the test should be licensed or certified by the manufacturer of the equipment on site. Those certified nationally by a recognized organization, and those certified by the state or local authority. And the test participants for this include representatives of. Oh, sorry. No, want to go to the next slide, Andrew. So the participants of the subject test, the human-based test, they're going to be more representatives of the building, the fire alarm system designer, the system equipment supplier, HJ installer, to get a mix of people to see if everyone understands the message being delivered. So it's very different in a sense where you have a group that is trying to hear the words, and there's a lot more human error in that, as opposed to an instrument that is actually going to be measuring that intelligibility on a scale that is essentially pass-fail. Can I go to the next slide, Andrew? So looking at what's acceptable, the best intelligibility, if we go back to the actual sound level, the best intelligibility is usually in that range of 70 to 80 decibels. But that's not going to mean that it's intelligible first. So the instruments that are being used, you're looking at getting your average for the entire space to have an STI level of 0.5, which by no means is perfect intelligibility, and having a minimum, 90% of the locations, the minimum being 0.45 STI throughout the space. The subject-based test is a little more unique in what is acceptable. There's no specifics in NFPA 72. Oftentimes, it's just seen as if you don't understand everything that's said in a space that's supposed to be intelligible, then you've failed the test. And so there's got to be a more stringent way, in that the instrument-based test kind of gives you that more quantifiable qualification for what is acceptable. So going to the next slide is just kind of a, again, kind of a graphical representation of what we were just talking about, in that your vertical axis here is your STI scale, and 0.5 being what meets, so the white area is compliant. And there's also looking at every instrument in itself has it's not standardized quite yet, so they all have different scales within them. So NFPA and sound engineers have established the common intelligibility scale, which helps relate STI and other different measurement scales of intelligibility as one common scale, and that's on the horizontal axis there. And so the passing or acceptable intelligibility is 0.7. So in a scale of 0 to 1, similar to what STI would be. And this CIS, the Common Intelligibility Scale, was developed in 1995 to show that relationship, because certainly if we didn't use STI, or if we did STI-PA, they are slightly different numbers that are coming up. So it depends on what your meter is set to for the measurements. So kind of looking at our next steps, we briefly talked about speech intelligibility software modeling. It's something that we have performed as requested within certain jurisdictions. However, it's not a code requirement, but certainly, as Andrew was talking about, it is very much recommended in certain environments, because it's difficult to achieve intelligibility when you have these unique and tough areas like tunnels. And that I also want to kind of put it out there for voice evacuation. These next steps, I mean, we're seeing a lot more of it because of the upcoming mass notification systems, and with some of the more recent code additions, the ability to integrate into the building paging system is key. And being able to integrate systems and minimize how much minimize costs to the owner. So to kind of summarize everything that we were talking about today, intelligibility is the ability to understand the voice message, not just hear it. So intelligibility is not audibility. And although EVACS are not required everywhere, it is strongly recommended in most occupancies. But there are certain environments that, as Andrew was alluding to, that it doesn't make sense, because it's either not achievable or it's very costly to achieve intelligibility, and it's not going to provide a safer environment for the occupants of the building. And always keep in mind the 5 factors for that affect intelligibility. Speech signal to noise ratio, reverberation, echoes, distortion, and most importantly, the human factor. And with that, we had some questions that were prepared ahead of time. I know we're coming down to the end of the hour here. So the first one here is, please spend some time discussing how to evaluate a space prior to completing the design for mass notification and your speaker type fire alarm notification. Our project involved a 200-foot long underground concrete tunnel with cast concrete floors, walls, and ceiling. Acoustics were terrible in that tunnel. So Andrew, can I address that one?
So that kind of pretty much relates to that subway unique environment that I was talking about earlier. I mean, in those situations, you really can't do a whole lot. You know, you could, if the tunnel is concrete walls, maybe you could work with the architect to provide some sort of acoustical covering on that concrete, or put a carpet down on the floor or something like that to try to help it along. Typically, it's what you can do with the regular basic notification appliances you get with all the systems that we specify is basically just reducing the spacing, more coverage cone overlap, and lowering the tap settings. So typically when you move the tap settings up, you're pushing the speaker, and you kind of get more noise when you move the tap settings up. So by lowering the tap settings and keeping the speakers spaced closer together, it provides a clearer, more intelligible signal. And then again, it goes with the if you see spaces like this during design, it's good to bring up these questions to the architect and the client, and try to figure out ways to attack it before it goes into construction, and to even look at a sound modeling or talk to a speaker consultant in order to maybe have them run a sound model on the tunnel to then specify use speaker that is better fit for the situation than your regular notification appliance that you would typically use.
Thanks, Andrew. The second question here was strategies for improving intelligibility when spaces fail. So as an engineer, I'm going to give the typical engineer response. Well, it depends, right? The improvements are based upon kind of the cause of the test failure. So distortion in the system is due to damaged or improperly installed equipment, which includes the wires exceeding the length, exceeding bending radiuses of cables, that sort of thing. So in that, there's stuff in the field that has to be reinstalled and fixed. If the issue is due to echoes and reverberations within the room, there are more architectural actions that need to be kind of taken to reduce the echoing and reverberation, which could be insulating materials that are applied to the ceilings, the walls. And if you catch it during design, which is what ideally our goal is when we're actually going through the sound modeling, is to tell the architect if they have ceiling heights that are causing an issue or geometrical features within the room that are causing the issue, and try to change those. Is something that can't be done afterwards, but you can close off spaces that may be causing the issue and that sort of thing to help with it. And kind of the last one here is kind of what Andrew was talking about, is kind of revising the spacing and output of the speakers. Speakers shouldn't kind of be just set to the highest rating. That doesn't necessarily give you intelligibility. It gives you audibility, but certainly doesn't give you the intelligibility that you're aiming for, and can actually have a tendency, if you put all of them on the high level, to distort the signal. So there's definitely a lot of different approaches there to achieve that if is a failure there. So it definitely has to be evaluated for each individual space. And the last question I had here is, are we now totally reliant on the AHJ's decision that an installed system is intelligible? And if the AHJ says they can't understand the message? The answer is no. As we kind of discussed in the testing methods section, there is the metering equipment that will allow you to determine if speech intelligibility is achieved. and within the acceptable limits. Going back to the STI, the CIS scales, we can base acceptance on those. At least in my opinion. I know obviously there might be some AJs on here that may disagree with that, but it's a discussion to be had. If the metering is indicating that's passing, that is something that is acceptable in accordance with NFPA 72. All right, so Jerry, that's all the questions I have here. I know there was some more, but we're kind of past the hour here now.
Sure. Well, Cameron, Andrew, really thank you for taking the time to pull together the presentation, spend some time presenting today. Can we possibly take some of those questions, maybe answer them offline and get back to the requesters?
Absolutely, absolutely.
All right, if so, that'd be great. I'll get those distributed out. So, all right, well, thanks again. Thanks everyone for joining. It's been great having you on, and look forward to, we have another event coming up in December. So look for an announcement there. Thank you.
Thank you.
Thanks, everyone.